Hello everyone, and welcome to our video on partial derivatives. So in simple terms, when we treat all variables except for one as constants and take a derivative with respect to only that variable, we call that derivative a partial derivative. Now, I should be clear, there's also implicit differentiation that can use partial derivatives, so it's not entirely accurate, but generally speaking, when we're doing partial derivatives, we're treating all variables as constants except for the one that we're concerned with. So if we take a look at some notation here, there's a lot of different equivalent notations for partial derivatives. Usually different notations are used in different contexts. So in differential equations, you often see this sort of operator notation, cap d of f, something like that is pretty common. Of course, df dx, well, that's actually not quite right. We're off to a good start. We got to do a little quick editing here. So let's just click in here. That should say partial. Okay, so little key extra thing here. When we're talking about partial derivatives, we write these curly Ds. All right, so those little curly Ds are to indicate that the derivative is only considering one of the variables and that your function actually has multiple variables. All right, now this notation here, f sub x of xy, we use this notation a lot to indicate partial derivatives, but in some ways it's kind of flawed, right? So we have to be pretty concerned if we're using subscripts for other purposes. So depending on the context, you may want to avoid this notation so that you don't confuse your function's partial derivatives with like f sub 1 or f sub 2 or something like that. So just try to keep in mind that you might want to change notations depending on the context of what you're doing to avoid confusion. Now, the formal definition of these partial derivatives looks just like the regular definition of the derivative, except that the distance h that you're talking about here only applies to the variable you're concerned with for the partial derivative. So the partial derivative of f with respect to x is the limit as h approaches 0 of f of x plus h y minus f of xy divided by h. So it should make sense that we said in this simple term segment here that we treat the other variables as constants because when we look at this derivative formula, the y coordinate isn't changing here. The only thing that's changing is the x coordinate. Now, if we look at the partial derivative with respect to y, well, first, what are our notations? We might have this cap d sub y of f, or cap d sub 2 of f. So this notation is meant to be read like the derivative of the second coordinate or second component of f, or the partial derivative of f with respect to y, or f sub y of xy. These are all equal to the limit of f of x, y plus h minus f of xy over h. So in this case, the only thing that's changing is your y coordinate. Okay, so what about second partial derivatives? Again, we've got a lot of notation options here, and we kind of just have to be careful with them. So one thing to keep in mind is that if we want the derivative of f with respect to x twice, so that's f sub x, which is f sub xx. So this is the partial derivative of f with respect to x twice. Now, it's important to keep in mind this parentheses here is implicit in this notation. So in this notation, the variable closest to f is the derivative we're taking first. And same thing here, f sub 1. But when we look at our partial notation here, it acts as an operator, so it's a little different. So here we have the partial derivative with respect to x of the partial derivative of f with respect to x. So in this case, the thing furthest to the right is actually the first thing because of the parentheses, right? There's this implied parentheses. And we notate this as d squared f dx squared. So you think this seems a little weird notation-wise, but you can think of reading it like this. The second derivative of f with respect to x twice. Right? So now let's take a look here. The derivative of f with respect to x and then y. So in this notation, the subscript notation, you've got f sub x sub y. So this reads f sub xy. On the other hand, for this partial derivative notation, it's the derivative with respect to y of the derivative of f with respect to x. So here, it's the second derivative of f with respect to x and then y. So here, your dx ends up on the right side because you're thinking of this in this parentheses notation. This is really just shorthand. Okay, so similar thing here if we have the derivative of f with respect to y and then x. So in the subscript notation, f sub y sub x, so f sub yx. And for this partial notation, your derivative of f with respect to y is first, so it's in the parentheses, and you apply the derivative with respect to x upon that. So in this notation, you get the derivative, the second derivative of f with respect to y, then x, your dy and dx being from right to left here. And finally, this last one is pretty self-explanatory, the derivative of f with respect to y twice. So that's exactly what you'd expect it to be. Okay, so now that we've gotten some notation out of the way, let's try to look at these things and see what they are. So intuitively, because they're derivatives and we've worked with derivatives for a long time, you should be thinking these are describing the direction of the output of f with respect to a variable, especially the first partial derivatives, we should say. So that is to say, how fast is the value of z changing when x or when y changes? So if we take a look at this model, which ignore the splotchiness, I couldn't quite get Blender to interpret this one properly, so it looks it's a little funny looking, but it'll get the job done. All right, so let's take a look at this thing here. So we've got this ellipsoid, and if we rotate this around here, I'll try to keep turning it. So what does this tell you? Well, we've got these two vectors. One's heading in the x direction, and the other's heading in the y direction. And of course, you would guess the one heading in the y direction is the partial derivative with respect to y. Well, I should say the vector associated with that partial derivative, and the one headed in the x direction is the vector associated with that partial derivative. So the partial derivatives themselves are just going to be the directions that the vectors are headed in, right? Just like the partial derivative of line is just this, or the first derivative of a line in 2D is just the slope. If we reframe this a little bit, they're a little awkward to move around here. So in other words, the slope of this vector is telling you the partial derivative with respect to x, and the slope of this vector is telling you the partial derivative with respect to y. So hopefully that makes some sense and helps make this idea of partial derivatives a little more intuitive. And it gives us some idea of the shape of the graph, the direction that the graph is heading. It tells us information about its velocity along a curve on this surface, so forth and so on. Okay, so let's go ahead and move on and do some computation here. Find the first partial derivatives of f of xy as given, x to the fourth power, y cubed, plus x squared times y. So first we'll take the partial derivative of f with respect to x. So all I do is I treat y as a constant in this case, and I treat x as my variable. Okay, so the derivative here is going to be 4x cubed And y is going to just be a constant, so it'll stay y cubed, plus, and here this derivative is going to be 2 times 8, that's 16x, and times y. And if we take the partial derivative with respect to y here, now we treat x and anything that's only dependent on x as just a constant, and we treat y as a variable. So we get 3y squared here, so 3x to the 4th y squared, plus, the derivative of y is just 1 here, so plus 8x squared. Okay, so that was pretty straightforward. Now let's tackle this second example. Find the first partial derivatives of u of r theta equal to sine of r times cosine of theta. All right, so we want the partial derivative of u with respect to r first. So we've got to apply the chain rule here. So that's going to give us the derivative of sine of this thing, which is cosine, times the inner derivative with respect to r. So that's cosine of r times cosine of theta times, now here, the derivative of r is just 1, and we treat this as a constant, so we just get cosine of theta. Now if we take the partial derivative of u with respect to theta, we get cosine of r times cosine of theta, and applying the chain rule gives us the partial with respect to theta of r times the inner function, right? R times cosine of theta. And so in this case, the derivative here, the r is going to be a constant, so that'll stay the same, and cosine of theta becomes negative sine, so we'll put that negative all the way out in front. So negative cosine of r times cosine of theta times r sine of theta. All right, let's take a look at another example. So this is the derivative of f, the second derivative of f with respect to y and then x. So to avoid confusion, I think it's oftentimes really helpful if you rewrite these. So the derivative with respect to x of the derivative of f with respect to y. So first, we need to find the derivative of this function with respect to y. Well, we first need to treat this like it's u squared instead of sine squared. So that gives us 2 times u, which is sine of mx plus ny, times, and now we need to take the derivative with respect to y of the inner function. In this case, u is my inner function, so that's sine of mx plus ny. So this becomes 2 sine of mx plus ny times, now the derivative of sine is cosine, so we get cosine of mx plus ny times the derivative with respect to y of this inner function, which is mx plus ny. And the derivative with respect to y of this is just going to be n, so I'm going to move that n up front. So this is 2n times sine of mx plus ny times cosine of mx plus ny. Now, the natural thing to do here would probably be to jump straight towards applying the product rule here and taking this derivative with respect to x. But if we notice that, hey, this 2 times this thing, like if I rewrite this as n times 2, this should look real familiar, right? So this should look like sine of 2 theta equals 2 sine of theta cosine of theta, right? The double angle formula for sine. So that's going to help out a lot here, because then I can write this as n times sine of 2mx plus 2ny. And that's going to be a whole lot easier to take the derivative of than that product. Okay, so here n is just a constant. The derivative of sine is cosine. And then the derivative of my inner function with respect to x is just going to be 2m. So this whole thing is 2mn times cosine of 2mx plus 2ny. All right, well, that's it for this example. Hopefully that was pretty clear. Now let's take a look at this example 4. So here we're going to take 2 partial derivatives using implicit differentiation. So here, instead of having a z as a function equal to f of xy, instead we have an equation involving all 3 variables, x, y, and z. But what we're saying here is that the function z is actually dependent on x and y. So we're not going to treat it as a constant. We'll treat it like we would in implicit differentiation. So let's start with our partial derivative with respect to x of both sides of the equation. So yz plus x ln of y, and the partial derivative with respect to x of z squared. All right, so this first partial derivative here, yz, y is going to be treated as a constant. Z is a function of x. So we get y times the derivative of z with respect to x. Plus, now here y is treated as a constant, and x is, of course, a variable in terms of x. So the derivative of x is 1, and we get left with just 1 times ln of y, which is ln of y. And here we have to apply the chain rule, because again, z is a function of x. So we get 2z times the derivative, the partial derivative of z with respect to x. So if we move this partial derivative to this side, we get ln of y equals 2z times the partial of z with respect to x minus y times the partial of z with respect to x. And if I factor dz dx, I can divide out the 2z minus y. So I'm skipping a little step here. But this gives us ln of y divided by 2z minus y equals the partial derivative of z with respect to x. So that's one of our partial derivatives. And let's go ahead and take the other. So same process here. Partial derivative with respect to y of both sides of the equation. Okay, here we've got y times z, and both are being treated as functions of y, so we have to apply the product rule here. So the derivative of y is going to be 1 times z plus y times the derivative of z with respect to y. Plus, and now this derivative here, we've got x times ln of y, so x is treated as a constant. So this is x times 1 over y, or x over y. And here we've got to apply the chain rule, and we get 2z times the partial of z with respect to y. Okay, let's do a little subtraction, moving things around here. So we've got z plus x over y equals 2z partial of z with respect to y minus y times the partial of z with respect to y. Again, I factor out dz dy. I get 2z minus y as my other factor, and I divide it, so I get z plus x over y divided by 2z minus y equals the partial derivative of z with respect to y. Okay, so hopefully that wasn't too bad there. Let's go ahead and move on to a theorem. So this is a theorem you should just kind of keep in the back of your head. It comes up, should come up later in this class as being fairly relevant to some problems. And I think it also comes up quite a bit in differential equations. Though it's been a while since I've taught differential equations, so I may be overstating its importance, but it definitely comes up from time to time. So suppose that f is defined on a disk D that contains the point AB. If the functions that are described by the partial derivative of f with respect to x then y, and the partial derivative of f with respect to y and then x are both continuous on D, then those partial derivatives at that point will be equal. So this is the key thing here. In general, we can't assume that these partial derivatives are equal. But if we know that those functions are both continuous, then their partial derivatives will be equal, and we can save us some computation time, at least computing at individual points. We'd still have to be able to check that both were continuous first. But once we have that, we can just plug in. Okay, so a little bit of discussion of some differential equations here. So since this isn't a physics class, I'm not going to, talk a whole lot about the experimental verifications of physics laws. But we will talk about a couple laws that are described by some differential equations. So this one is Laplace's equation. It's given by the second partial derivative of u with respect to x twice, plus the second partial derivative of u with respect to y twice equals 0. And solutions to this equation are called harmonic functions, and they have applications in heat conduction, fluid flow, and electric potential. So let's just take a look here, and we'll show that this function, e to the x times sine of y, is a solution to Laplace's differential equation. So first we'll take the partial derivative of u with respect to x. And that's simple. E to the x, its derivative is e to the x, and sine of y we treat as a constant. And so if I take the derivative again, so this is my second derivative with respect to x, I'm just going to get e to the x times sine of y again. Now let's take the partial derivative of u with respect to y. Well, the derivative of sine of y is cosine of y. This becomes e to the x cosine of y. And hence the second partial derivative is negative e to the x sine of y. So if I take these partial derivatives and I add them, I get e to the x sine of y minus e to the x sine of y, which is exactly 0. All right. Now let's take a look at one more example here. So this is called the wave equation. So this is a partial differential equation that describes the behavior, the expected behavior of waves. So here, a is some sort of constant that modulates the impact of time here, like how fast a wave is moving, essentially. And so what this equation should represent is like the height of a point on the wave, but it's not with respect to two position coordinates. Instead, it's with respect to a single position coordinate, like say a distance from shore, and also the time, because you might be looking 10 meters out from the shore, and the height of the wave at that point is going to be different depending on what time it is, right? So if you think about it that way, so we just want to show here that the sine function, sine of x minus at, satisfies the wave equation. All right, well, let's take our first derivative of u with respect to t. So if we're taking this with respect to t, we get cosine of x minus at, and the derivative of the inner function will just be negative a. And then when I take my second derivative, derivative of cosine will be negative sine times, and the chain rule is going to give me another negative a here. So these negative a times negative a is a squared. Put that in front, and it's all negative a squared sine of x minus at. Now if we take the partial derivative with respect to x, okay, what do we get here? We get cosine of x minus at. And if we applied the chain rule, the derivative of the inside would just be 1, so we can skip that. Now we take our second derivative, and we get negative sine of x minus at. And that implies exactly what we wanted, that the second derivative of u with respect to t squared is equal to a squared times the second derivative of u with respect to x squared. Done. All right, well, that's going to be it for this section on partial derivatives, so thank you for watching.